Okay, so before we can actually find the trig form of a complex number, we need to talk about what a complex number is. So any complex number is just a two-dimensional point where x is considered the real number and y is considered the imaginary. So any xy pair can be rewritten as an imaginary number or a complex number, I apologize, by simply separating the values and putting an I with whatever your y coordinate was. So the point P, for example, if we say is, I don't know, 2, 4, this would be the same as the complex number 2 plus 4i. The same thing would apply if I had a point Q that was the point, I don't know, 1, negative 3. Changing that into a complex number, that would be 1 minus 3i. Your x coordinate is always the real portion. Your y coordinate is always the imaginary portion. Which means if I were to graph these two complex numbers, my x-axis would correspond to whatever my real number is. My y-axis then would correspond to whatever my imaginary number is. So it graphs exactly the same. We're just technically replacing our axes with real and imaginary values instead of x and y. Is everybody okay with how to take a point and rewrite it as a complex number? Anybody not see how we changed these? Yes, it will always be I because I is the imaginary portion. So I'm going to give you one to change yourself, and then we'll move on. So this will be point R, and it is going to be 0, negative 11. And I would like for you to rewrite that as a complex number. Ismail, what'd you come up with?
0 minus 11i.
0 minus 11i, or since the real part is 0, we can actually leave that off, and this could just be negative 11i. It is your choice if you want to leave it like this or put it like this. It doesn't really matter. This can also go the other direction. For example, if I were to give you a complex number such as, I don't know, let's say negative 2 plus 7i, and I wanted to rewrite that as an xy coordinate pair. My x coordinate would be my real number part, negative 2. My y coordinate would be my imaginary part, positive 7. Anybody confused on how we can change them from an xy coordinate pair to a complex number or the other direction? Everybody okay with that? So let's talk about complex numbers in general. When I'm talking about a complex number, I usually write it as complex number z. So we can have an infinite number of z's. So z1 could be a complex number, z2 then would be a different complex number, z3 would be another complex number. We usually pretty much always use z, and for all of our examples today, we will. Just as a refresher, in a complex number, the first number is the real portion or the real part. The second number with the I attached to it is the imaginary part. When we talk about absolute values, they still have a length, sorry, not absolute value, a complex number. They still have a length to them just like vectors do, except now instead of calling it magnitude, We call it the absolute value of a complex number. So the absolute value of a complex number is the distance from that number to the origin 0, 0. We can find the absolute value of it by taking the square root of our real part squared plus our imaginary part squared. So it's still the distance formula, just like magnitude is, and it still represents a length or a measurement from the origin to that complex number on the graph. So I like to say that this is equivalent to magnitude. When we talk about this length for a complex number, instead of 2 absolute value lines on each side, we just use 1. So what we're going to do is we're just going to practice finding this absolute value or this distance with different complex numbers. So for these examples, we're going to find the absolute value for the given complex numbers. The first one we're going to start with is 2 minus 6i. And I would like to find the absolute value of that complex number. To symbolize that, the first thing I'm going to do is I'm going to put an absolute value sign around the number itself. And then I'm going to set that equal to the square root of my real part squared plus my imaginary part squared. And then I'm going to simplify. Bless you. Just like we did with magnitudes before, if it doesn't come out to a perfect square, we leave it under the radical. You can reduce it, but it's kind of no point. You're welcome to if you would like to, Gabe.
I don't really want to, but we just don't.
Any questions on that? Is anybody struggling with finding that absolute value distance for a given complex number? No, because it's exactly the same as magnitude for a vector, and we've been doing that for like a week. Let's go ahead and do another one, and by let's, I mean you.
But you don't do anything with the left at all.
What do you mean with the left?
Would it be that? Or that's the value. You don't do anything.
We did it.
Should just show
This is the absolute value of that. Yeah, the absolute value is literally just that distance from the origin to that complex number on the graph. It is the exact same as magnitude. They just use different words because a complex number doesn't have direction or speed or anything. So this one is yours to do on your own. I would like for you to find the absolute value of the complex number 0 plus 3i. Alexa, walk me through it. What'd you say, honey? Can you talk louder? Okay. So my A is 0. You don't have to put it because I know 0 squared is still 0. And then what did we do with the 3i? Square rooted it or squared it? Square it. Then we do the math and add it together. I get the square root of 9, which is just 3. Anybody confused there? Everybody get 3 as the absolute value of that complex number. Anybody not get 3? Anybody not see how we got 3? How many of you are bored out of your minds? Okay, somebody, I like it, I like it. Okay, so what we're gonna do now is we're going to take these complex numbers and we are going to change them into the trigonometric or polar form of that same complex number. So when we're going to do that, there's a couple things we need to find first to make that conversion. Like the whole thing? Or just this little piece? No, not much space at all. So the trigonometric or polar form of a complex number z is equal to r times the quantity cosine of theta plus sine of theta I. This is also equivalent to r times cosine of theta plus I sine of theta. So different people like to put the I in different places. It doesn't really matter as long as it stays attached to the sine. Okay, because that's technically my imaginary part. I know we've really missed these thetas and these trig functions, so I'm glad I was able to bring it back for you.
What is the R?
Where is it?
What is it?
I'm going to tell you in a second. Everybody have these two written down, or whichever one you prefer. For the purposes of today, I like to keep the I at the end, but you're more than welcome to put it in front of the sign if that's how you like it better. So to write this trigonometric form of a complex number, there are 2 pieces of information I need to have. I need to have the R, and I need to have the theta. So what I'm going to do now is I'm going to show you what we use to find that R and to find that theta, and then we're going to practice making the conversion. So the good news is we already found what R is equal to, and that is whatever the absolute value is of my original complex number. So the absolute value of the complex number I started with is my R value. In other words, it's the distance from the origin to my complex number. In order to find my theta, I need to think about trig functions in general, specifically tangent. So before, I knew that tangent was equal to y over x. In a complex number, I no longer have y and x. Instead, I have a and b. So this is actually equal to b over a, where b again is the imaginary part of my number and a is the real part, which means to find theta, I'm going to have to do tangent inverse of b over a. Just like previously where we were doing inverses, this is going to give me 2, sometimes 3, sometimes 4 different angles that could possibly work. And I'm going to have to find the one that is in the correct quadrant as my original complex number. Okay? So again, the 2 pieces of information we need are R, and R is just the absolute value of my complex number, which is what we were just doing above. And then to find theta, I do tangent inverse of b over a. And then I find the angle that matches the quadrant I need it to be in. So let's do an example. So we're going to start with -4 plus 4i. This is going to be the complex number that I would like to change into the trigonometric form of that complex number. In order to do that, what 2 pieces of information do I need to find? Or absolute value, which is R, and what? Theta. So I need the angle, and I need that measurement, that length, that distance. So I need R and I need theta. Which one would you like to solve for first? R. R, I know, is simply the absolute value of the complex number that I was given, which means this is equal to the square root of my first number squared plus my second number squared. And then I reduce it. Negative 4 squared is 16, 4 squared is 16, 16 plus 16 is 32. That is not a perfect square, so I'm not really worried about reducing it, which means my R value is simply the square root of 32. Anybody have issues with that? Everybody okay with how we got that? Okay, you will need your unit circle for this next part. I'll give you guys a second to get that out. I will also tell you that when in doubt, I like to do all of my angles in radians instead of degrees. I do. However, I would let you do whatever you are most comfortable with unless I specified it on the homework. Okay, so if you want to do degrees, you can do degrees. If you want to do radians, you can do radians. But all of my examples, except for a couple, will be in radians. Everybody have their unit circle out? Hopefully, yes. What?
There was ice in your sweatshirt pocket that was unmelted.
Okay.
I'm confused about the unmelting this part.
It's
So
still
unmelting or like
It's melting right now, but like it was in there.
I was wondering why, yeah, it's all wet.
Oh my gosh. Okay, everybody have their unit circle out.
I drink badly.
Awesome. Let's find theta.
It has two on the chart.
I'll show you. Okay, so I know my theta is equal to tangent inverse of b over a. My b value here is positive 4. My a value is negative 4. So I have tangent inverse of 4 over negative 4. I know the fraction 4 over negative 4 is not on my unit circle, but I can reduce that. And when I reduce that, it becomes tangent inverse of negative 1. And I know that value is on my unit circle. I actually have two thetas that give me a tangent value of negative 1. What are they? 3 pi over 4 and 7 pi over 4. So the ultimate question here is how do I figure out which one of these I'm supposed to use? Because I can't use more than one, or I'm not going to use more than one. Look at the signs of the number I started with. My first number corresponds to my x-axis. Was it positive or negative? Negative, which means from the origin, I went left. Was my y value positive or negative?
positive.
Positive, so I went left and I went up, putting me in which quadrant on the unit circle?
2.
Which one of these two is in quadrant 2? So that's the one that I'm going to be using. I have my theta, I have my r. Let's change this into the trigonometric form of its complex number. So that this is equal to my r value, which is the square root of 32, times the quantity cosine of 3 pi over 4 plus sine of 3 pi over 4 I.
Alright, we'll use degrees, but just not right now.
You are able to use degrees, yes. I will use radians because I like them better. But if you put degrees, as long as it was correct, I'd be okay. So if you wanted, that would be, what, 135 degrees?
And that's what is that starting from going?
Yeah, this is it. This is your answer.
Oh.
Because I was just asking you to change it into the trigonometric form. Yes, Jojo. I went to -1 for like back of your unit circle. Tangent column, followed it down until I found -1. I found it in two places. I found it at 3 pi over 4 and at 7 pi over 4. Okay, do you remember when we did that with trig inverses before? Same idea. How do we feel about this? Good. Anybody super duper confused or worried about not understanding it? Let's do another one. This? Yes, this is your trig form. So this next one, I'm actually going to let, no, I won't won't let you do it on your own yet. You're gonna want my help for this one. So this time I have the complex number 2 root 3 minus 2i. How am I going to start this one? Solve for r. What is r equal to here, Becca? So it's going to be the square root of my first term squared plus my second term squared. What's 2 root 3 squared?
Square root of 12.
12. We square the 2. We square the square root. When I square the 2, it becomes a 4. Square the square root, it becomes a 3. 4 times 3 is 12. Negative 2 squared is 4. So I get the square root of 16, which just equals 4. So my r value here is 4. Everybody okay with that?
So 2 times square root of 3 was 2 separate values, right?
Mm-hmm.
Wouldn't it FOIL it?
No, because there's not addition happening between them. So technically what I did is I just took this square and I distributed it to each of the values inside. Like that. If there was addition or subtraction between them, yes, I would have to FOIL. But they're technically still one term because they're connected by multiplication. Okay. Any other questions on that R1? Now I need to find theta. So when I find my theta or set it up, I'm going to have tangent inverse of what over what?
2 over 2 square root of 3.
Negative 2 over 2 square root of 3. That I know does not show up on my unit circle, so I'm going to have to reduce it. What reduces here? The 2's. So this becomes tangent inverse of negative 1 over the square root of 3. Is that on your unit circle anywhere? In a different form. So we rationalized it, which means we take the square root of 3 and try to eliminate it from the denominator by multiplying it into the top and the bottom. So in rationalized form, this actually looks like negative square root of 3 over 3. So this is the value that we're looking for on the unit circle, and I'm looking for it in the tangent column. Just like before, we are going to get 2 different thetas, and we're going to have to determine which one we're going to use. When you have one, raise your hand. Becca, what's one that you found? What's another one, Nadia? 1 pi over 6. So again, we run into the issue. I have 2 different angles that satisfy this tangent value. How do I determine which one I need to use? What quadrant will this point be in?
Quadrant 4.
Quadrant 4. How did you know that, Ismail?
Because it was positive and I went down. So I went to the right.
X was positive, so I went to the right. Y was negative, so I went down. The quadrant to the right and down from 0, 0 is these 2 angles exist in quadrant 4.
11 pi over 6.
11 pi over 6, so that's the theta that I'm going to be using here. I have my theta, I have my r. Let's go ahead and write our trig form of this complex number. And then we're finished. Questions, concerns, or issues thus far? Let's do another one. actually like for you guys to do this one on your own.
That's great.
What can I do? Like,
Yes. I'm just kidding.
really?
Either.
What are you confused on?
I don't know how to reduce.
You have the R or the theta?
the theta.
Okay, pause there. Right, how do I find my R value here? And that comes out to be what? Show of hands, who else got the square root of 53 as your R value? Perfect. No issues there, right? Is Melanie an issue or a question?
Oh, no.
No,
sorry.
okay.
Just go back.
How many of you, however, ran into an issue with your theta value? Should have been all of you. Okay? Because when I go to do my theta, I get tangent inverse of 7 over 2. That's bad. Or not bad, but that's not easy. First of all, 7 over 2 does not reduce. There's no pi in it either. I don't know why I said pi. Don't need pi in it. That's not a value that's anywhere in my unit circle. At least it's not a value that we identified as being on our unit circle. That doesn't mean it doesn't exist. It's just not going to be a nice, pretty, whole number degree that we easily recognize. When you get something like this that's not existent on our chart, we are going to work in degrees because it's going to be so much easier. So what I'm going to do is I'm actually going to use my calculator for this one. And we're going to do tangent inverse of 7 over 2 and see what we come up with.
Wait, but that doesn't make sense.
Why does
Oh,
that
no,
make
it
sense?
doesn't.
Yeah.
Oh, I decimal place.
If I'm changing this into a degree angle, what mode should your calculator be in?
Degree.
Degree, and we are okay taking it to the 10th place here.
Dude,
Yes.
I don't even remember how to do this.
Tangent inverse of 7 over 2, exactly how it is right there.
Oh,
Okay.
So that was much more complicated.
What angle did we come up with?
74.05.
So 74.1. Who else got 74.1 degrees? Okay. So here's the super duper fun part. There's actually more than one angle on the unit circle that would give me this tangent value, but I don't necessarily need to find it if this angle's in the correct quadrant for my complex number. So I check that first before I look for other angles. So 74.1 is in which quadrant?
First quadrant.
Quadrant 1 is my complex number in quadrant 1.
Yes.
How do we know that?
Both positive.
They're both positive. So that means from the origin, I moved right 2 and up 7, which puts me in quadrant 1, which means that 74.1 is going to be the angle that would work. If it's not the angle that would work, we would just add 180 to find another angle on the circle that gives me the same tangent value. Yes. So this one works, and I have my R value, which means I'm ready to rewrite this in its correct trigonometric form. And when I do, it's going to be the square root of 53 times cosine of 74.1 degrees plus sine of 74.1 degrees I. Yes, ma'am. No, you can do it in degrees every time. I do it in radians because I like that better. But you guys, unless I say you have to do it in radians, you're welcome to do it in either form. Yes.
Can degrees be exponentialized over time?
Unless the directions say otherwise, that's fine.
Okay.
Yeah. Okay, any major questions, concerns, or issues with that one? What if I would have gotten a negative angle?
Subtract that from 360.
Not subtract. I could add 360 to it, or I could add 180 to it, and then add 180 again to get my two angles. Okay, so anytime you get a negative or we get one that doesn't work, start by adding 180 to it because that's the period of tangent. Okay? Not the period, but close enough. Okay. So what we're going to do now is we're actually going to give this one a break. If you do need another example, there is one on the notes that you're welcome to look at, and it is one that gave me a negative angle to begin with. So that's a really good one for you to work through on your own. What we're going to do now is we're going to practice multiplying and dividing complex numbers, and then that is the last portion of these notes. We're probably not going to get through all of it today, but we might have one example left for tomorrow.
If we're not gonna get through all of it, can we do the other?
Do we want to?
I mean, if we're already not gonna get through it.
Oh, I mean, we can get through a good chunk of the multiplying and dividing one.
You could just leave it all for tomorrow. So it's
But then you don't have homework time and quiz readiness time for Thursday.
I say we just skip the one question.
I say that you guys are perfectly fine and going back and looking at this one on your own. It's a really good one for you to do. Just know if you get a negative, add 360 to make it positive. Okay? So this is by far more important than doing that one example. We call this computing with complex numbers. For these examples, we are going to assume that we have two complex numbers, z1 and z2, where z1 is r1 cosine theta 1 plus theta 2. Oh gosh, no. I can't erase on here. There we go. Sorry. Cosine theta 1 plus sine theta 1 I. And then z2 is the same thing, but with 2. So r2 cosine theta 2 plus sine theta 2 I.
We're gonna have 2 points.
The first thing we're going to do is we're going to write out the multiplication of two vectors and then the division of two vectors, and then we will do, not vectors, complex numbers, and then we will do some examples of actual numbers in place of these R1s and R2s and whatnot. So what happens when we multiply two of these complex numbers together? So for example, if I wanted Z1 times Z2, the first thing we would do is we would multiply our two R values together times the cosine of my angles added together plus sine of my angles added together, I.
what?
That's what would happen if I multiplied together two complex numbers.
Are we talking about like the real and the imaginary numbers, like multiplying those together?
Or even in trig form, same thing would happen. But we are keeping them originally in their a plus bi form. That's how we're starting it.
Did you just combine my terms? Or like that?
But even that, if I took that multiplication and changed it to this, it's still going to come out to this. Okay. Okay, so what happens then if I divide them? What do you think is going to happen?
Subtract.
Subtraction's going to happen. So this would be Z1 over Z2, and this is going to be R1 over R2. So the R value from the first complex number divided by the R value from the second complex number times cosine of the first angle minus the second angle plus sine of the first angle minus the second angle. when you're doing the division, order really does matter here. So we count anything from the top complex number as my ones, anything from the bottom complex number as my twos. So let's do one with actual numbers. The first example, yeah. The first example will be multiplication. The second example will be division. So this says if z1 or my first complex number is equal to 2 root 3 minus 2i, and z2 or my second complex number is equal to negative 1 plus root 3i, part A asks me to find the product or the multiplication of those two complex numbers. Huh? I would like to do it using that formula that we wrote out just above this. So for that formula, I need to know the r from the first complex number and the angle theta from the first complex number. And I need to know the r from the second complex number and the angle theta from the second complex number. So I basically have to do separate work for these before I can put them together. So we're going to find all of this information for the first complex number z1 first. We're going to start with the r. How do I find the r for that first complex number? What thingy, Colin?
Yeah, just square root both of them. Square root both of them.
Okay. So we're going to square each of the parts of that first complex number, add them together, and then square root the answer. So when I square 2 root 3, I already know that I get 12. When I square negative 2, I already know that I get 4, which leaves me with the square root of 16, which just equals 4. So R1 here is going to equal 4. Now I need to find my theta for that first complex number. I know that's going to be tangent inverse of negative 2 over 2 square root of 3. Of course, I can go ahead and reduce that by taking out the 2's. I get tangent inverse of negative 1 over the square root of 3, and I have to rationalize it. And I end up with tangent inverse of negative root 3 over 3. I believe we already did the work for this one on one of the previous examples. So I know that this is going to give me two angles. It's going to give me 11 pi over 6 and 5 pi over 6. Which one of those two angles exists in the same quadrant as my original complex number? 11 pi over 6, because that is in quadrant 4, and so is 11 pi over 6. So that's going to be my theta 1 here. So theta 1 is 11 pi over 6. R1 is 4. Now do all of this again for complex number 2. The good news is once we do this work here, we can use it for part B as well.
Just a little much. I'm just going to find this fun.
I do find this one, it's enjoyable. So doing all the work, we should get that the R value for complex number 2 is 2, and the theta value is 2 pi over 3. I just looked on my unit circle, or on the chart on the back. Yes.
When I 30 degrees, it gives me negative 60 degrees.
So add 360 to that,
I got so
or 2 pi over 3, or for 11 pi over 6.
I just got 300 degrees on my calculator.
Which one did you plug it into?
Oh, I plugged in that.
You did this one?
Yeah.
Very down the wrong one. No, it's 2 pi over 3. Then you needed to add 180 to that. That's why.
Oh.
Yeah, sorry. I thought you were just changing it. For the purpose of this one, it might actually be beneficial if you change these to degrees instead of keeping them in radians, since we're going to be adding and subtracting them. If you want to keep them in radians, that's fine, but you're going to have to find like common denominators and everything. And I know you guys don't really like that much. So 11 pi over 6 is equal to what degree? What's 11 pi over 6 equal to in degrees? Say it louder. 330. And then what is 2 pi over 3 equal to in degrees? That's going to make it much easier to compute with. So now what we're going to do is we're going to take these R values and these thetas and plug them into that multiplication formula that we have. That multiplication formula, again, says Z1 times Z2 is equal to R1, R2, cosine of theta 1 plus theta 2 plus sine of theta 1 plus theta 2i. Filling all of these in, we get 4 times 2 times cosine of 330 plus 120 plus sine of 330 plus 120i, and then we'll simplify it.
We like to use dots again.
You can do yeah, you can use dots for multiplication now, because these aren't pointers. Anybody not get 8 cosine 450 plus sine 450i? Yes, what'd you get?
It's because I looked my 2 as my R2 was a radical 2. I don't know.
What did you?
Like
Well, you should have gotten root 3 squared is 3 plus 1 squared is 4, square root of 4 is 2.
Oh,
Yeah.
I left the I in there, like
Oh,
square root
okay.
of 3
Yeah.
I squared, so I got negative 3.
Don't do that. Anybody not getting this? We're gonna pause here. Come right back to this
Dude, on
example
that one
tomorrow.
example, man,
Well, if you hadn't like said it, maybe we could have finished this one.
Thank you.
No, I'm